The topic of this video is the compute shader, which we can find here in the GLSL top. If you've used GLSL in TouchDesigner before, chances are that you used the vertex or the pixel shader, but we also have the compute shader. In the GLSL mat, we also have the geometry shader, but that would be a topic for another video. And the difference between the compute shader and the others is that it doesn't go through the rendering pipeline. And out of these three, it's probably more closely related to the pixel shader. So they have some similarities, but they have different purposes. So what is the compute shader for? It allows us to use the GPU to compute things. It can be anything. It doesn't have to be related to 3D or to image processing. And this is also called GPU, or a general purpose use of the GPU. The architecture of the GPU makes it really good at calculating things in parallel. So if you provide it with a data structure that it understands, it can calculate things faster than the CPU. Let's take this example of a nested for loop. For every x in a range between 0 and 1920, go to every y in a range between 0 and 1080, and then do something. And this means that do something is called 2,073,600 times, and this can put a strain on the CPU. For the GPU, this wouldn't be much of a problem, assuming that do something is something that we can write in a way that it understands. So that is a lot of processing power, and the way to access that power is via the compute shader. Now, it is true that it is also possible to use the pixel shader to compute things, but there are some advantages for the compute shader. And again, as I mentioned, it doesn't go through the same rendering pipeline. So this means that it doesn't have to worry about vertex assembly or tessellation or rasterization or depth test or output test or anything like that. The pixels are read directly, and this means more speed. So let's see how we can use the compute shader. Let's delete these two and start from fresh file. We can drop a GLSL top. Here under mode, switch to compute shader, and immediately we get a warning which says that compute shaders require GLSL 4.30 or later. So we need to change the GLSL version here to 4.30. Now we want to hide our pixel shader and reveal the compute shader, which is here. We can click on edit to open an external text editor. Make this a bit bigger. And get rid of these comments. And let's move this commented outline up here, and here for vec color, let's declare it and assign it on the same line. So now we only have these two lines to worry about, and we can see what they're doing. They're just giving us a full white square here. So we're declaring a color which is full white, and then we're calling a function, and that's all that this is doing. The function is imageStore, which means we're writing to an image, and it takes three parameters. First one is the index of the output that we're writing to, or the index of the color buffer. So it's writing to the first one. We can see here in our GLSL top that we have a number of color buffers, and it can go up to 10, or in my case, if I go anywhere beyond 8, I get a warning. So this is the limit of my graphics card. I'm going to leave it as 1 for now. Now the second parameter, it is similar to the UV coordinate if you've used the texture function in pixel shader. The difference is that this is not in the 0 to 1 space. This is in the pixel space, which means it goes to 0, or from 0 to the width minus 1 of the image, and then from 0 to the height minus 1 of the image. And we can see that if I type just 0, 0 here, save it, we can see that we're writing to the very first pixel here at the bottom left of the image. If I change this to, let's say, 90, then it's going to go to the 10th pixel here on this first row here on the x-axis. Let's revert back to what we had before. And the last parameter here is just the color. So if you use the pixel shader, you're familiar with this. This is the same as the output frag color that we write. Now let's have a look at this line here at the top, which describes the local size. And in order to explain that, let me use an illustration. Imagine that our output image has 8 by 8 pixels, and I want to split this image into smaller groups. Let's say 2 per axis, so 2 on the x-axis and 2 on the y-axis. Now inside every group, I have 4 by 4 pixels. So these groups here in purple are called work groups, and the size of each group is called local size. The groups are like threads, and the local size is the size of each kernel inside the thread. Let's see how we can define them in TouchDesigner. We've already seen in the shader file that the local size is defined here. So in this case, we have local size of 8 by 8. And the work groups are defined here in the dispatch size parameter. At the moment, we have 64 by 64. And in order to see what this means, let's say we multiply 64 by 8 and we get 512. So let's change the size of our shader here to something bigger than that. Let's say 1024 by 1024. And now we can see that we only cover 1/4 of the image with our white pixels. And that's because we don't have enough work groups to cover the entire image. Let's change that to, say, 128 on the y-axis. Now 1 to 8 multiplied by 8 is 1024, and we cover the whole area. The same would be true for the y-axis, of course. But let's go back to 64 by 64, and instead of changing this here, go to our shader. Let's change this to 16. So now our local size is 16. Obviously, we get the same effect. But in order to decide when to use more groups or a bigger local size, that would depend on the application of your shader. For example, if you're writing a shader to calculate Gaussian blur, you might want your local size to be the number of pixels neighboring a given pixel. Another thing you might want to take into account are the limitations of your graphics card, the maximum number of work groups and the maximum group size, but these tend to be quite high numbers, so we're not going to worry about this at the moment. Just going to go back to 8 by 8 here, and for our dispatch size we want something relative to the size of image that we're using, so let's store that in a constant. Just drop a constant top. Call this size. It's going to be a square, so width and height are going to be the same. Just going to set it to 256 and use value here. Now we can copy this expression, and here in the dispatch size we know that our local size is 8, so we can just paste our size and divide it by 8 and do it twice for x and y. 32 times 8 is 256, and we have enough to cover the entire image. Now let's go back to the other line which is commented out. Let's uncomment it and drag it after the declaration of the variable color. And what this is doing, it is reading the pixels from a texture, but not using the texture function. We're using texelFetch. And the first parameter is the input texture. The second, we've already seen it. These are the coordinates in pixel space. and the third is the level of detail, and we're fine with 0. So now let's save this, and we get an error, and that is because we don't have any inputs attached to this GLSL top. So let's attach something here. I'm going to use a noise top. Let's connect it here. Just change monochrome and switch it off so that we have some color. Now we can see that the output of our compute shader is identical to the first input. Now let's copy this noise, paste it. Let's just change it to something else, random. Then connect it to the second input. And we can also read the color from this. Here, let's change. Well, we can delete this color here and just call this one color A, and then we pass it as color A. Now I can duplicate this line, call it color B. Going to read from index 1, and we duplicate this line and we write to the output 1 plus color B. I'll save this, get another error, and that is because we only have one color buffer. So let's change this to 2. And in order to see the second buffer, we need a render select. Let's drop our render select here, and we want to read from GLSL 1, so drag it on top. And now we can see color buffer index 1 is our second input. We change this to 0, we get our first input. So let's just copy and paste render select so that we can see both. Okay, next let's have a look at pixel formats. Go to our noise here. You can see that our pixel format is 8-bit fixed RGBA. And in order to see the difference that it makes if we change the pixel format, let's use some geometry. I'm going to drop an add sop, and let's toggle add points to add a point, and then let's connect a convert sop, and we want to convert to particles per point, and we want the particle type to be render as point sprites. Now let's drop a null. Then middle click and drop a geometry comp. We also want a material so we can see the geometry. So let's drop a point sprite matte, drag it on top, select material, and then here in the geometry comp, let's toggle instancing, and let's use our render select here as translate op. Then we pick R, G, and B. Now you can see we have this kind of cube made of particles here, and this might be what you want, but maybe you are not expecting this sort of result from the noise. Let's see what happens if we change the pixel format to 32-bit float. You can see we have quite a different result here. So this is just a reminder to pay attention to pixel formats when using compute shaders, because it changes the results quite dramatically. Okay, now moving on, there's another thing I want to mention, which is how to read from a texture which has dimensions which are different to the other input textures or to the output of our compute shader. Let's drop a movie file in top and pick an image. I'm going to select the trillium, and I'm going to attach to the third input here. We can edit our shader again, just duplicate these lines, so call it color C, index 2, then write to the output index 2 and pass color C. change the number of color buffers to 3, and we want to copy and paste this render select pointed to index 2. We can see that it is reading something from the trillium, but only a portion of the image. In fact, only this bottom left portion here. That is because the trillium is 1280 by 720 and our output is only 256 by 256. So in order to read the entire image, we need to calculate the ratio between these two. The TouchDesigner already passes something to the shader which helps us do that. So let's click on the help button, then click on write a GLSL top and go to built-in uniforms. You can see that it passes a few uniforms there, and one of them is this TDTexInfo with the index of the input. So this is an array, and it's an array of this type here, TDTexInfo, which is described up here. It contains two vectors. One is the resolution of the input and the other is the depth. In the resolution we get both width and height, and also 1 divided by width and 1 divided by height to help us with the calculations. So let's use this. Let's create a new variable here, which is going to be a vec2 I want to call ratio, and this is going to be UTD_infos and I pass index 0. Then I get .res for the resolution, and I take xy, which is 1 divided by width and 1 divided by height. And then I divide this by UTD_infos index 2, and then the same .res.xy. And now if I multiply my coordinates here by this ratio and save it, let's see what it does. Now we can see that we are reading from the entire image. Obviously the aspect is wrong, but that is because we are using our output aspect. Actually, we're calculating the ratio between this image and this image, which are both inputs. But we can also use the ratio of the output. Let's go back to the documentation, and we can see that we have another TDTexInfo here called UTD_output_info. So let's use that. Let's copy it and just replace this UTD_info 0 here. Paste it, save it, and the output is the same. And now one last thing that I wanted to mention is that TDTexInfo allows you to use texture instead of texelFetch for reading from an input. We can use it to calculate UV coordinates in the 0 to 1 space by dividing our working pixel coordinate here by the total resolution of the input. So let's create another variable, vec2, let's call it UVC so that we know that we're using color C, and it's going to be GL_global invocation ID.xy divided by UTD_infos and then index 2 res ZW. So we take the last two components, width and height, and we save this. Actually, we want to comment out the texelFetch line here, and let's replace it with vec4 color C texture, and then we pass the same input, so std inputs 2, and pass our newly created UVC. I save this, and now we can see we went back to that first situation with just a portion of the image, and that is because we're not using our ratio, but we can see that it is already working correctly. Let's also multiply our UV by the ratio we calculated, save it, and we are reading the full image exactly like the texelFetch. And you might have noticed that I used the last two components here, and I divided this by the last two. If I change this and just multiply by xy, the result is the same. So I think that's it. just wanted to give you an overview of the compute shader and how to use it in TouchDesigner. This is not a particular useful network, but I hope the concepts that I mentioned here were useful. I have another video planned where I'm going to show an effect using the compute shader, so that was going to be a bit more practical. But yeah, I hope this was useful. If you have any questions, feel free to ask in the comments. Otherwise, until the next video.